All right, welcome back, everybody. This is ET210 and a lecture that is on solar and Solar Lab 1, and also on a little bit of Blackboard. So I had some problems with Blackboard last week, so things got a little mucked up. I've reorganized, and I want you to spend some time in there kind of understanding where we're at. Great job on watching the movie for the first and second hour. So the third hour is coming up, in which you'll post about. So that'll probably be on Wednesday. I have combined the folder for 3 and 4 here. And if you click on it, you'll see that it goes all the way back to Wednesday and then Friday. And then today, Monday the 24th. So on today, you'll see this lecture. You'll also see Solar Lab 1 that I want you to do. And some other information, solar angle calculator, which you're going to use. And this is the solar irradiation from NASA, which we'll talk about in a second. But those are some sites that can be beneficial. So I updated the calendar. Oh my. I love it when it does that. It only does this in student view, so I'm really not sure, but that's all right. We can handle it, right? So I've updated the calendar, and the solar lecture is coming today. I don't think it got released. If it did, I'm sorry about the redundancy, but Solar Lab will be today. And I think I made that due the 28th. So you have some time to work through this. And then Solar Lab 2 will be on the 26th, and then we will have a quiz on the 1st. So none of that got released last week. So not sure really what happened, but I'll blame it all on the holiday. How's that? All right. So moving forward, I'll try to keep things more organized. I did put up 3 jobs that are available for students. So some of you are second-year students. If you're interested in any of these, reach out to the contact person for more information. They're fantastic opportunities. Everybody's hurting for help. So if you are at all are interested in Daimler Trucks or Pacific Core, or a small civil engineering firm, I think called Geotech. Yeah, I'm not sure. There we go, geotechnical. But check out the last one here. That's a company called Pacific Core, and look at his title. Manager of Substation Engineering. So this is a person involved with a lot of electrical concepts. So kind of like we're discussing right now. All right, enough of that. Hopefully that, better organizes that information. I did go through and do some grading. So you all did a great job on that, on those discussion postings. So this time you're going to have a little more to do, but I want to start with my PowerPoint. So I'm going to stop this share and do a new share. And this is going to be on solar. So I'm not going to go super deep into it, but kind of hit it on the surface level and then do some calculating with it. So our top 5 renewables, photovoltaics, which most people call solar energy, but solar can come to us in other ways like solar thermal. So the top 2 are sun producing alternative energy sources, then wind, biomass, and geothermal. So we'll do all of these. Hydro can be in there too, but it's not as available to the world as it is to local applications of hydro. Like we have here in the Pacific Northwest, we have a lot of hydro. And it is renewable as long as we don't consider taking dams out, right? Because dams are what produce the energy. So, all right. So let's talk about PVs. So there are a number of different kinds of photovoltaic cells, and these cells make up panels. So each panel will consist of a few different cells. They can be up to 50 cells or even 100 cells in a panel, or it can be as small as 10 cells in a panel. There's different kind of crystalline structures in these panels, and the basic three are monocrystalline, meaning that those are all the same and they are created that way. So the crystals are similar, all of the same type. Okay, the polycrystalline, they are consisting of different kinds of crystals, and that is a cheaper method of producing solar panels. The ones we have in the lab are polycrystalline. They're less efficient, down in the 14% range. The monocrystalline are more expensive and a little more efficient, 16%. That means that we're capturing 16% of the energy that's hitting the panel. Not very good, yet it's still a very good production of energy. So we'll talk about that when we talk about solar irradiation, how much energy comes to the planet from the sun. And the last one is amorphous. Amorphous is a man-made crystal, so not a natural crystalline process. All right, so how's it work? The basic concept of a crystalline structure is a structure that has both positive and negative conductors in the system, in the crystal, and that there are holes in either the positive or the negative side. And when the sun hits the panel, it activates those holes and encourages an electron to jump. So the definition is solar cells are made up of these semiconductors, right? Generally silicone, which is sand, in which the photoelectric effect takes place. This effect consists of the transfer of energy to the valence electrons. So those are the vacated or empty electrons, right? So they break their bond and they can jump into these holes. So when the sun radiation hits the crystal, these little electrons jump, and that is current. When we get electrons, photons jumping, that is the flow of current. All right, my phone on. I need to stop that so it doesn't do that anymore. Sorry about that. All right, so you set that up as best you can in the structure, you know, as cheaply as possible. We can make it a lot more efficient, but it's not cost effective. Okay, so you know, an example of these panels. This is pricing from several years ago, but it's fairly current. Like the price hasn't dropped a whole bunch. This is an 80-watt monocrystalline off-grid solar panel. So off-grid is the same as on-grid, really, as far as solar panels go, but it might have some wiring that is a little more user-friendly for an off-grid application. But you can see the price, $346 for an 80-watt. 80 watts, not much. And then you can see what kind of amperage we get. That's maximum power current at 4.54. So that's pretty low amps. Like if you think about your home and the amperage that you can carry in just a basic circuit in your home, which is 120 volt, that's like 15 or 20 amps, right? So this is 80 watts, pretty low wattage, and pretty low amperage. In other words, not a lot of current is flowing. And that's typical. That's why we have arrays of these things to up the amperage and up the wattage. Okay. All right. So, you know, here's a 4-pack, I guess, for $1,000. So 265 watt panel. So you can do the multiplication. We're looking at about 1,000 kilowatts there, a little more than 1,000 kilowatts for $1,000. So you can kind of get, you know, a cost. Now, on average, a Portland home is going to need about 1,000 kilowatts, not watts. 1,000 watts. So an electrified home uses a lot of wattage. All right. So that's really what I want to, you know, emphasize at this point. All right. Actually, I'm just going to keep this small. Not exactly sure what your view looks like. I'm in a little bit of a split screen, so hopefully you're able to see everything just fine. All right, I'll make myself even smaller. There we go. Maybe lower it down a little bit. All right, So the acronyms that we're going to use are listed. So PV systems and electrical conversion, we have to think about a number of different things. And we'll kind of define these as we go through the course. I'll start with watts. Watts is how we measure energy, and watts is per unit time. So watt is not just an energy amount, but it is an energy per unit time. So when you say 60 watts, that's some kind of a time consumption. Like a 60-watt light bulb, when you screw it in, you turn it on, turn it off, that wasn't 60 watts, right? That was a 60-watt light bulb for 1 second. So watts typically means like an hourly per hour usage. You're going to produce 60 watts. All right. But we'll get into that, into more detail in that as we go through. Voltage is kind of the operating system. So 120 volts is like your home, right? That's the normal operating system. Europe has different voltage. Solar has different voltage. Solar is a 12-volt system typically. So the voltage coming off of your solar panel is 12 volt typically, okay? So it might be 200 watts, but it's at 12 volts. So that's a different amount of power. And power is like what we can use, right? That's the strength of it. Amperage, I, is the flowing river of electricity. Like how much flow do we have? Is it a really small amount of flow that can go through a really small wire? Or is it a whole bunch of flow that we really want to produce that needs to go through a big wire? So a lot of times amperage also is called current. So that's the next question there. Is like the amount of water flowing in a river, the amount of electricity flowing in a wire. And, you know, if the river's not big enough, we can't push more water through it. So if the wire's not big enough, we can't push more current and amperage through it. We just can't do it. So that's a limiting factor to whatever we have going. All right. So the last thing is resistance. That's anything that's kind of impeding the flow of electricity. And then kilowatt we kind of talked about, that's 1,000 watts. All right. So let's keep going. I'm not going to go into calculations. What I want to focus on is this diagram and your lab 1. So what you're going to do in lab 1 is you're going to use this information, the sun angle positioning, and I'll click on that in a second. Hopefully it'll go to it and you can see it. But I'll make sure that you can see it, even if I have to stop sharing. But what you're going to find out through this sun angle calculator is the angle of the sun today, or whatever day you do it, tomorrow or the next day, just put a note on there. You're going to calculate the angle of that sun as close to noon as possible, okay? So that'll be from the angle finder. And I'll kind of show you how that works. But you're also required to do it by experimentation. So experimentation can be, and I'm going to try to show this to you on my whiteboard. So we'll see if this works. I'm going to stop sharing. Yeah, so you can kind of see it. I can't really get to it with my earbuds in, but maybe I can scoot you a little forward. That should affect the camera. All right, so I'm going to right up here. I'm going to try and, pick a spot where you can see it, but you take one earbud out. Hopefully that still works. So what you're going to do is on, a good sunny day, the sun is going to send rays to the earth, right? And you're going to position yourself in the sun with an object. So you need to know the height of the object, whatever it is, a board, a book, anything, but you need to be able to measure the height. So you're gonna put an object vertical, and you know the height, right? Let's see if maybe black shows up a little bit. Let's say height equals 12 inches. Yeah, that shows up a little better if it writes 12 inches, right? So then in the sun, that's going to make a shadow. So do this at a specific time, close to noon, and we're going to have many sunny days in a row, so you should be able to pull this off. But then you're going to want to measure the shadow. So that produces a shadow. Can't make it right anymore. Black is going away. So I'm going to go away. All right, black looks so good. Stop. All right, green. All right, so green, yep, works. That produces a shadow. So let's say the shadow is 36 inches. Because the sun's kind of low in the sky. It's this January, right? So middle of the winter. It's not good. Doesn't get very hot. But through that, you should be able to, between the 36 and the 12, you should be able to calculate an angle with trigonometry. Now, that's the solar angle. That's the angle between the sun ray and the horizontal surface that you're standing on. So we're going to call this the solar angle, right? Now, it's not the angle we would set the solar panel to, right? The solar panel we would want set perpendicular to. So that is going to get set at a different angle. But all you're going to calculate is the solar angle. So let's see, I think I have another diagram for you, but that you'll get that by experimentation. And then write it up, kind of put it on a piece of paper, give me a drawing and show me how you calculate it. Okay. All right. So let's go back to the share. Oh my, there's a lot of them. Okay. We'll try this one. All right. That works. So then as I move forward, I'll come back to this and we'll operate that. Oh, this is not what I want. I thought I had it back. Sorry. Oh yeah, here it is. Okay, so here's a little more complicated conversation about what we just did. But you can see that data, the bottom one, the solar altitude, is also what we're calling the solar angle. So it gets referred to different ways. We're not going to worry about any shifts right and left. We're just going to try and come up with that solar altitude. Okay. But there is other information there. So, all right, so let's go back. Here's even a more complicated view of it. This is the solar panel. And you know, why they have the sun over here, I'm not quite sure. I think the sun should be over here, normal to the collector surface. But for some reason, they seem to be putting it parallel to the panel. That's a little odd. But again, you'll see these different diagrams for the same thing. We want to know really the angle between the sun and the earth, because then we would put the panel perpendicular to that. All right, let me go back a little bit and just talk about a few more things. I will come back to this solar angle positioning link and see how that works. All right, so let me just talk about the production a little bit of a solar panel. That's something you should need to know, or you should know. And it doesn't happen throughout the day, right? We get the most production when the sun is perpendicular to the panel. So the panel gets set either for a winter set or a summer set or somewhere in between, if it's not adjustable. Now, there's a lot of adjustable systems out there now. That's becoming more efficient. But the production time is going to be a narrow slot. I mean, there will be production, you know, between the 6 and 8 hour. But the big production happens between the 10 and the 14 hour on this graph. And that's a typical graph. And that's like watts per meter squared. So a lot of times we're going to talk per meter squared. All right. This is different kinds. This is a nice slide on kind of the hierarchy of a solar panel. Starts with a cell, right? Single cell, that's these guys. And then you'll have a single module, and then you line modules up and you'll come up with an array. So that's good terminology. All right, let me just cruise forward a little bit. There's other information in here, but I don't really want to talk about it. Here's another picture of kind of the solar radiation coming from the sun. So the irradiance, it's called irradiance up here. That's how much energy actually comes to the surface. So the irradiation is enormous. The amount of energy that comes from the sun to a surface is incredible. And it has been proven that that amount of energy just from the sun that hits the planet every day is easily enough energy to supply all of the energy required for the planet. Everything. Easily, like room to spare. The problem is capturing it, and the problem is storing it. But you'll hear this from solar advocates. All the energy we ever need comes from the sun. We just need to be able to capture it and use it. And that's true. That is an absolute fact. Okay? You cannot say that about wind. The wind doesn't blow that often. You can't say that about geothermal. You can't say that about hydro. Okay? You can say it about the sun. It sends, look at these numbers, it sends an enormous amount of energy. This A is how much energy comes per square meter. Square meter is not that big on these different days. Like it's enormous. You know how many square meters there are on the planet? A lot. So, you know, it's super exciting energy source. We just need to be able to fine tune it. Okay, here's another just a simple example. This would be on a fixed surface. So this is on like a solar panel, right? 6:45, we get nothing. Then the sun comes up at a weird angle. We get very little. Then at noon, the panel's probably set for perpendicular there. It's where we get the most production, and then it tapers off. So that's kind of what we're looking at with photovoltaic solar. There are other types for sure. All right, let me go back to the angle calculator and let's see if we can get this going. I'm going to stop sharing and then kind of minimize this. And so you probably can't see this yet, but just hang up with me. Let's see if I can get to this thing. So bear with me. You can even fast forward a little bit. Now I'm going to try to screen capture it just to make sure you can get it. Okay, so that link is working, and this is the sun angle tool. So this is a pretty nice one. This is from Sun Design. This is a solar company, but you can use it a lot of different ways. So it's kind of fun. You can look it up by zip code. So I can just put in a zip code. I'll put in the colleges, 97030. All right. So look up. So it uses that zip code to put in information. Okay. It's got the time in for me. It still wants me to input a time, so I can do that. I'm going to say 12. And I'm going to say PM because that, oh, let's go 24-hour clock. That's even better. So now I'm pretty close to noon. This is what it used for latitude, longitude. That's fine. If I know my exact latitude, longitude, I can put that in. But I don't. So I'm just going to use this, right? Now, it does want to know what day of the month. So I've asked you to do it on June 21st, which is the summer solstice, and do it again at December 21st, which is the winter solstice. You know, you can make the year more current if you want. It should be able to forecast forward, hopefully. Let's see if it can. And then the elevation. So the elevation of the college is about 250 feet. You can use that if you want. So 250, because that does change the angle of the sun, right? It absolutely would. So then if I hit calculate, it's going to run some numbers for me. So you're going to do this also. So make sure you do it. I'm just going to change the date just so we get some weird time. So this is March 21st, right? And I'm going to hit no daylight savings time. Time basis is clock time. That's fine. Hit calculate. So boom, it crunches it out. Now, what's really nice about Well, one of the things really nice about the sun calculator is you can just click on one of the numbers to learn about it. So it's calling this the altitude angle. It's saying 44.81 degrees, but if you click on this, it'll show you what it is. And guess what? That's exactly what we want, is that altitude angle. So pretty fun. It gives it to you for a specific day and a specific time. And then you'll compare this to your Solar Lab. And that's what you will submit as Solar Lab 1. All right, that's enough. Sorry about the debacle last week. We'll get in a regular flow of lecture and do some things from here on out, hopefully. So I will stay in touch with you. And if you have any questions, please send me an email and I can get those answered. I can produce a little video if you want, or I can, make changes in Blackboard if something's not done. All right, fantastic. Good luck, and let me know how it goes.